Hello, everyone. Thanks for joining. I know how exhausting those Zoom meetings are. It's Thursday afternoon, a full week of conferences underway. So thanks for attending. I'm Bernhard Klingenberg, and I'm here to talk to you about something that connects to the theme of engaging everyone, because I used this engaging everyone idea a long time ago, many years ago, when I started designing apps for introductory statistics education. And I want to present some of those apps to you today. Each of these apps that I'm going to show you is sort of dedicated to a specific task that you would see in an introductory statistics course. And it's sort of my version of moving the statistics education, or at least doing statistics, into the cloud. Now, my idea was to, by providing such tools, to engage the students both inside and outside of the class, and at the same time provide teachers with some really cool tools to introduce various topics and concepts. Now, I call this talk Seeing is Believing, because to me, the ideas that we teach and the concepts that we cover in our introductory statistics courses, they come to life when we can see and feel and interact with them. And that generates believing, and that generates buy-in. So that was a big motivation for engaging students and writing those apps. Now, once students feel and see those ideas and concepts, they become more memorable, I think, when we can interact with them and when we have activities that are connected to them. And so I will talk briefly about how you can do those using any of the apps I'm showing today. And then lastly, the apps are also there to make it relevant for students so they can use it to analyze their own data. And I'll show that again. All right, now in the about 20 minutes I have, I'll show you a couple of apps. I'm going to start with a very simple one, and probably an app that you've seen in various disguises in your course, and you've probably used yourself, and that's to showcase what it means to what a sample-to-sample variability is all about. One of our biggest and the most important concepts of how we can use sample-to-sample variability and the whole idea of a sampling distribution to estimate parameters, to give point estimates and interval estimates. So I'll start with them, and then I'll move on to two other ones. I'll show you not right now, but this is an interactive session. So I actually encourage you to go along with me and join me as I'm now going to the site www.artofstat.com/webapps. And I think Carrie is going to put this in the chat, so you can just click on that. And that's what I'm doing here as well. I'll just click on the app and go to the link. And now I need to see if I need to share my screen again, or if it looks okay and you can actually see what I'm seeing on my screen.
We can only see your slides right now.
You can see my slides. So hold on a second. I'll just change to my browser. Here we are.
And the link is in the chat, so anyone can go there.
Perfect. I think by now you should see a web browser opening up. That's when you click on the link. And so I'll go to the one. You have to scroll down a little bit. So this is at, if you want to go there, at artofstat.com/webapps.html. You can put this into your link. What I want to show is you have to scroll down a little bit till you get to what I call sampling distributions and the central limit theorem. And there is the first app I want to show you is one about the sampling distribution for the sample mean for a continuous population. So I'll just click on that one, and it will open up an app. And you've seen those before, and I think actually on Tuesday I saw someone from Jump show something very similar. But here's a nice idea that I think is really neat. Instead of simulating drawing samples from some theoretical distribution, which you can do here, there are uniform distributions in here. There are skewed distributions in here, skewed population distributions in here, and there are bell shapes where you can vary your things. But I think a neat idea really is to use real population data when you showcase what it means to repeatedly simulate from a population distribution. So I'm actually not going to use the default one, which is about, I think, student depth, but I'm going to use one that is about Airbnb prices. So what you see in the picture here is a real population distribution of more than 47,000 listings from 2019 on the Airbnb website for rooms to rent in New York City. And I put up one filter. I said the room has to cost less than $500. So here are all the rooms that were ever listed on Airbnb in 2019. So that's a real population, and you can actually see all the values here going all the way up to 499. So that's what you should use, or what would be nice to use as your real population distribution. And you see the population mean is roughly $130, and you see the population standard deviation is roughly $85. And now you can use the app to do various things. This is what I mean, seeing theory in action. You can click on draw samples to draw a sample of various sizes. Let's actually start with a sample of size just 10. Suppose we just look at 10 rooms. Those might be the 10 rooms that Airbnb by default just randomly puts on your site if you go there and look for rooms in New York, rooms for rent in New York City. So you press there once or twice and 3 times, and now you really see what sampling to sampling variability means as you watch that this blue triangle that indicates where the sample mean from my sample falls relative to the population mean, and how it hovers around, sometimes being close to it, sometimes being far away from it, to the left and to the right, and so forth. And that will give students an idea of what sampling variability is, and then you can increase the number of simulations you run until you finally a picture emerges that depicts the sampling distribution. And then, as I mentioned, you get students' engagement and be more memorable the more you engage them and design activities around such apps. Now, take, for instance, the slider and increase the sample size, watch what's happening, and you can explain, ask students to explain what they see happening, the variability getting smaller, the shape changing, and so forth. So that's one thing of engaging the students. You also have the samples down here, and there's various other things I don't have time to go into you can do. But I really like this idea of having real population data up here as your distribution, as your population distribution to sample from. Now, sample-to-sample variability doesn't just happen for continuous distribution like the price here. It also happens for discrete distributions. And so a similar concept, I'm going to get out of this one and go back to the Art of Stat website, still looking for sampling distributions, is when you have a continuous a discrete population distribution. And again, here the idea of using real population data seems really attractive. What you'll see as the app starts up, and again, you can follow me if you want to, it's showing a distribution that's just centered on 5 values. This is the Amazon star rating on a particular prominent or well-rated item called a Fitbit wristband. And the population distribution you see here is based on the user rating of more than, I think, 40,000 users who gave that Fitbit wristband a rating. And of those 40,000 users, which I now consider the population of raters, 23% gave it a 1-star rating, 11% gave it a 2 or 3-star rating, 13% gave it a 4-star rating, and 42% gave it a 5-star rating. And so that's our population we sample from. And we can take samples of size 10, for instance. We just sample randomly. We select 10 users at random, see what their star reviews was equal to. You can see the sample you got here. And again, see how the sample mean, the average review, the average number of stars that the reviewers gave, how that varies around the population mean. And again, you can do the same thing that we did before. You sort of slowly see the sampling distribution build up. And then you can ask your students various things about them. What happens as the sample size increases? What happens to the standard deviation? What happens to the mean of that distribution, and so forth. All right, so those were 2 sort of basic apps that you probably have seen in one way or another before. Now, before I go to the next demonstration, demonstrating a new app, I actually want to ask you a little question. And so if you can get a poll up, that would be great. I was actually wondering, what is the statistic that you think your students are most likely to encounter in their daily lives? And I give you a couple of options there. Which one do you think? Which statistics, as engaged citizens, your students, once they are done with your statistics course, are the one is the one that they're most likely to encounter. And I only let you choose one here. I know that's limiting. Probably you would like to choose 2 or 3 options, but I ask you to just narrow it down to the one statistic you see that you think students will encounter the most or see the most of in their lives. And I know that I realize that's a very broad question, but maybe you can indicate one of these options here. All right. Let's close the poll and see, can we actually get results? Because I currently, so overall, most of you, well, not most, but 45% think a proportion, that's right. But that's not quite what I, from my own perspective, see. There's a big vote for correlation as well. To me, and that's interesting, only 1%. The ratio of proportions, really interesting. To me, that is the most common statistic. As I go through, my daily life, just this morning, coming here to think and prepare my talk, maybe I'm listening to NPR too much, but again, I heard this word, 2 groups. One was twice as likely. I think this was in terms of unemployment benefits. Blacks are twice as likely to apply for unemployment benefits in the recent crisis compared to whites, or Hispanics. So I think we're 1.5 times as likely to employ for unemployment benefits. So wherever I go, I see that's twice as likely, half as likely. I see the ratio of proportions all the time. And so maybe you do too after not being made more aware of it. I didn't actually think that only 1% of you would choose this. Anyway, so this is my next topic. I want to talk a little bit about the ratio of proportion, because I do think it comes up all the time in the media, in political science, in certainly in medicine, and in public health a lot. And so I have an app for that one too. So I'm going to close this out and go back to, maybe I just go back to the top so you can orient yourself under the Art of Stat website on the web apps. If you just scroll down a little bit, there's a whole block of apps that are there for illustrating association. And so the very first one is called the association between 2 categorical variables. And I'll quickly mention what I want to do with this one. I'll choose a data set that's quite interesting, which is about eyewitness testimony. And so what happened in this, for this data set over this trial, I'll show you that the raw data set in a second. What you see there is there were a total of 373 participants in that study, of which 190 were assigned to watch a video which of a robbery of a grocery store. And they watched not the video of the robbery, but they watched the video of the trial. So there was a defendant that was put to trial, and that trial included strong eyewitness testimony. And so the actors acted out the trial, and at the end, those 190 who were assigned to watch the video that included the video of the trial that included strong eyewitness testimony, they were asked to vote, is the defendant guilty or not guilty? And 42 of the 190 said it was the defendant was guilty. And then 183 participants in that trial were assigned to view the video of the trial that now, of the same setup, same robbery, same other circumstantial evidences, but now included a weak eyewitness testimony. And of those, 38 found the defendant guilty, and the rest did not find him guilty. Now, the data are organized in a contingency table here, and you see them here as well. Of course, as soon as you see data organized in a contingency table, you want to look about conditional sample proportions. So of those watching the trial that included strong eyewitness testimony, roughly 22% said the defendant was guilty. And of those watching the trial that included weak evidence, only around, 21%. This line here, 21% found the defendant guilty. You have the sample proportions shown or displayed in a bar chart here, and then you can see the difference of proportion is computed by default. It's only 1 percentage point, right? 0.01. So that's 1 percentage point difference, not very much. That's the difference between 22% and roughly 21%. But often, when we hear, and that was the case for this article as well, on which this trial reported on, we don't compare two proportions in terms of their difference. We often compare them in terms of their ratio. So let's look at the ratio of proportions, which is simply 0.2211 divided by 0.207, and that turns out to be 1.06. And what does that mean? This is one of the major things I focus on early in my introductory statistics course, where the initial weeks are just spent on exploring and explaining data. So a ratio of proportion, often called a risk ratio, of 1.06 just means that those who watch the trial or watch the video of the trial with the strong evidence were 6% more likely to find the defendant guilty than those who watched the video with the weak evidence. 6% more likely. That's maybe not very much. So you can go a little bit further maybe and ask, well, what would you assume that ratio to be if there was no association, no relationship between the type of video the people watched and the verdict they delivered? Well, then these proportions will be the same in theory or very similar in practice, and that means this ratio of proportions would be just very, very close to 1. Is it close to 1? Well, here's sort of what I said before in the introduction. Just playing around a little bit with the apps might give the students some appreciation of what they're doing. For instance, how can we get this closer to 1, although it might already seem close to 1, if we just, for instance, move 2 observations, right, from those who found the defendant not guilty to guilty, of those who saw the video with the weak evidence, like make this 40, and I can go in here and just put in a 40 in here. Suppose that's for 40. So just 2 people decided otherwise. This should be now 143. Then we get a ratio that's pretty close to 1. And so we see it just moving 2 people along out of 183 really sort of tells us that the ratio doesn't seem to be that far from 1 if you take sample to sample variability into account. Now, I'm going to quickly go back to the original data. If you want, you can go further. If you already talked about margin of errors and a little bit of inference, you can click on, and I purposefully didn't put this right there. I said you have to ask for it. For inference, you'll see, well, if you try to estimate the population parameter, the ratio of the guilty verdict, the proportion of people delivering a guilty verdict in the entire population, if those had seen those 2 types of videos, we estimate that to be 1.06. And here's a confidence interval for it that includes 1. So 1 is a potential value, is a plausible value for that proportion. So perhaps there's not a difference between the proportion of people delivering a guilty verdict between those seeing the video with the strong eyewitness testimony and those with the weak eyewitness testimony. Now, if you do want to go a little bit further, I don't have too much time today, but you can figure out the confidence interval on your own. There is a Bootstrap tab on the app that lets you simulate taking samples here by using the Bootstrap from the population. Here is approximated by the observed data and what could happen. Although I should say this interval here is not based on bootstrapping. This is based on some other theory that works pretty well. But you can go to Bootstrap route too, and just you see the original data here, and you just generate Bootstrap samples showing or highlighting those persons who actually have been selected to be included in the Bootstrap sample. And then what you see on the other side is the Bootstrap sample, the contingency table that results from that Bootstrap sample, the conditional proportions, and then here you can watch the ratio as I click on this, how that changes as I take Bootstrap samples from the original data, from the contingency table. And down there you can watch the Bootstrap sampling distribution build up. And there's various other options you can do, such as finding a percentile confidence interval, which I can go into here, and then you see what that amounts to, and it seems to be pretty similar to what the interval I've showed you before. So that was a plug for the ratio of proportion. There is another wrinkle to this whole data set. I'll show you the data set in a second, but they didn't only do videos with strong and weak evidence, they also actually gave the people instructions before they saw the video, and those are either standard instructions that every one who serves in a trial will get. And then there were some new instructions, and those new instructions actually emphasized the role of eyewitness testimony more. And now you see, if you look at those data, now it seems that of those who saw the video, of those people who saw the video of the trial and received the standard instructions, 27%, or roughly actually 28%, found the defendant guilty. But of those who actually saw the video but received the new version of the instructions of how to actually incorporate eyewitness testimony, only 15% found the defendant guilty. So that's now a ratio proportion of 1.847. So the proportion of guilty verdicts for those who received the standard instructions is now 84%, or roughly actually 85% higher compared to those who saw or who received the new instructions. And then the confidence interval now does not include 1, and you can talk more about that one. If you actually, and I mentioned in the introduction, it would be nice, or it makes it more memorable if students can incorporate their own data. So I want to quickly demonstrate you can do this too. You can either just put in your own data here, or you can type in data here, or if you have your data, and I need to just quickly see if I can share my screen. I gotta move these out. So you can see the actual data set again. Where's my share screen? There we are, new share. An Excel spreadsheet, I think you should see now. This is actually the raw data set of the contingency tables I showed you before. As you go down, you see the person 1 through all the way down to 373, and some information about those people. And the last column gives the verdict. Here's the instruction type. It's coded here control and new instead of standard and new. And here's the testimony. Those were the things we talked about. But you can actually just grab, for any data set you have, like this one in an Excel spreadsheet, you could just grab your data, your raw data, and paste it into the app. And then the app will do the summary for you. So I'm just controlling and pasting this one. And now going back to, let me switch the screen back again, going back to the app, and then I'll just click on the first cell here, and I'm now just copying and pasting the data in there. I should probably have to give it name, instruction for the first column, and verdict for the second column, and then you can submit that, and then you can do the same thing that I demonstrated before. So that's good for students to do. They can use their own data, their own projects, bring them into the app, and do the kind of things you probably demoed on prepared data in class or online now, because we don't meet in class anymore. All right, finally, I think I have just a little bit left. One very quick thing I want to share of how to do inference, because it was so remarkable that just in March, every government of every country was chasing or trying to estimate this one parameter that was so important during the COVID crisis. And we had, and I think, Carrie, you were part of a nice COVID-19 panel that talked about how to bring COVID-19 into the classroom. I did bring it into the classroom using one example. I'll show you the example if I can switch my screen. It is right here. So this was interesting. In March, right, every government tried to race to try to predict the proportion of their people in their country that actually is infected with the virus, with the SARS-2 virus. But all the data they had was not very useful, because testing was in short supply, and only those people who actually showed symptoms were tested. And so those data were useless in actually predicting or trying to predict the true proportion of a country's population who was infected. There are, and so making inference was pretty impossible. You couldn't do inference because there were no random samples available. But Iceland actually was one of the very first nations, and then followed by Austria, my own home country, that actually tried to get a random sample of people and test them all and see how many of them are infected. And so Iceland, between March 13 and March 21st, 2020, managed to test roughly 5,500 people, of which 48 actually tested positive for the virus. And so you can then ask your typical questions you would ask in an introductory course: estimate the proportion, give a margin of error, find a 95% confidence interval. And I'll just quickly want to show you how easy that is to do with an app. So I'm going to go back to the collection of apps I have up there, scroll down a little bit, or all the way down to where we actually can do inference. And I'm going to use the one where it says inference for a proportion. Click on this one, and then maybe here just provide the number, the sample size. And it was too short for you to see. But it was 5,571 people that were actually tested in Iceland, and of those, only 48 tested positive. And then that will give you your confidence interval, and that was surprisingly small. So it ranged from 0.6% to 1.1%. So that's the range. That's the 95% confidence interval for the proportion of people who were actually infected in Iceland at that time. And then the app, right, there's lots of things. It gives you the standard output of standard errors, margin of error. You can play around and with the confidence level and see how that affects your type of inference. You can have lower or upper bounds instead of interval on the confidence level. There's various things you can do. You can even do, if you so desire, do significance tests and put in, suppose this is the null value you hypothesized before seeing the data, like the Icelandic government believing that 1% of people were infected, and then would come to conclusions. So again, this is using your own data and then using the apps to just make your data come alive and make those concepts you've covered, be it confidence interval, speed, p-value, just come to life and being more interactive. I guess I'm going to stop here to show you more apps. Let me quickly go back and share my last slides, because I want to ask you to encourage you to give feedback in the question and answer session. And if you're interested in the eyewitness testimony that I mentioned briefly, here's the link to the article. That's the title of the article, and you can search on it on PLOS ONE. Okay, thank you very much.
Great. Well, thank you, Bernhard. These apps are fantastic. And we do have some comments and questions. One person is just a praise. I cannot imagine teaching sampling distribution without this app. I've used it in the past, and it really helps students understand the developing histogram resulting from repeated samplings. Thank you. But nothing for you to respond to, just a praise.
Thanks.
Next question. The app seems to work fine for me on Chrome, but I'm unable to open the apps on Firefox. Have you seen this problem before? Maybe it's just a problem with my preferences.
Interesting. I've not seen that problem before. I tried out many browsers, and it even like iPads even. Interesting. Maybe can I just encourage that person to get in contact with me? That would be great.
Great.
It should work. It should be browser independent. I think that's the hope.
Next question. Will this website always be available to those who are not using the textbook?
Oh, definitely, yes. The website is really almost independent of the textbook. I do use data that I talk about and that I screenshot in the textbook, but the website is there for everyone to use. Yes, certainly.
Thank you. Next question. Sorry, can you please repeat where the COVID example was? Was it on the same page as the apps?
The COVID example is going to appear in the app. This was one I just really, I think, designed, was it 2 or 3 weeks ago when I did the final exam for my class. So it was going to appear in the app. The example, the screenshot you saw, this is coming out in the new edition of the textbook, so it will be in there, but I'll make sure I include it in the app. It's really just a simple random sample of 5,571 people, of which 48 tested positive of the virus.
Okay,
yes.
Great. Well, thank you so much. There's one more question. It just says, can you put the resources link in the chat box? But I think, do you just want that art of stat posted again? Is that the link you want? Otherwise, I will let you post whatever link you want to post. And I want to again say thank you to Bernhard for a fantastic presentation.